want to talk today about why there are stable orbits in a gravitationally bound system. If we look at something like the Earth-Sun system, which you can see here, very not to scale, the Earth goes around the Sun and it stays in a more or less circular path. And so we would think that somewhere there has to be a minimum of energy that the Earth goes to. Just like if we have a skateboarder on a ramp, he's going to go down towards the minimum area of energy, especially if he keeps losing energy to friction. So the Earth's path should be more or less along that line of minimum energy because everything in the universe tends towards a minimum of energy. So this should be easy to find, right? We just take the equation for the gravitational potential energy and we plot that and we get this line here. I think we can easily see the minimum energy is right along that left-hand side where the Sun is. That's our zero radius. If we put that on our old picture, then our minimum energy is right in the middle of the Sun. So if we want to put the Earth on our diagram, we can easily see that it'll go towards the minimum energy and dive straight into the Sun, which is not what happens in the real world, and that's no good. So let's look at where we may have oversimplified things a little bit. This is a one-dimensional view. There's our dimension blinking red, that's the radius from the center of the Sun. And that whole coordinate axis is rotating. If we draw it on our picture, we can see it spinning around the Sun because we're keeping track of where the planet is in terms of distance from the Sun. So anytime I see something spinning or rotating, I think, well, maybe there's a centrifugal force involved. And you may be saying, wait, I heard that the centrifugal force was not a real thing. Well, if we're inside a rotating coordinate system, as we are in our setup, then the centrifugal force is in fact a real force. It's only from an outside perspective that we can realize that the centrifugal force is really just inertia. So in our system, the centrifugal force is perfectly good to use. So like I said, we have a centrifugal force. I'm going to rewrite that so it's in terms of the angular momentum rather than the velocity, because the velocity changes during the orbit and the angular momentum doesn't. I can use an integral to create a potential energy out of this force. And I get this UC value in the lower right, which is my centrifugal potential energy. If I graph this equation, then I get this shape, and if I add together my two energies, if I take my gravitational potential energy and my centrifugal potential energy, I can add those two together and get a total potential energy for this system, which is this line in blue. And this line has a really nice feature that the minimum energy is not at r equals 0. It's at some radius from the Sun. And so if I watch the Earth in that orbit, it'll move around in that circle, staying in the area of minimum energy. We can also see from the curvature of the graph that this is a stable equilibrium. So if we have a planet that's in an elongated elliptical orbit, its energy will still oscillate around that minimum energy. So everything we learned when we first studied energy about how objects like to go to the point of lowest energy is still true. And when we consider both the centrifugal energy and the gravitational potential energy, we can find that minimum.